Okay, welcome back, everyone. So it's a pleasure to have the second talk today by Neil Lambert from King's College, who's going to tell us about the non-Lorentzian view of the M5-brane, so the M theory point of view. Neil.
Okay, hi. Well, first of all, I would very much like to thank Hisham and all the other organizers for inviting me to come back here. It's a very nice place to have a conference, especially at this time of year. And I've decided to stay at the podium. They've got this microphone, but I fear that if I use it, I will break out in song, and that will be no fun for anybody. So I'm going to stick here, if you don't mind, and use the latest modern technology like that. So I want to talk to you about work that I've been doing, and I've been doing it over, well, some would say decades, but the particular set of work I've been doing in the last few years with a set of authors, collaborators, I should say, listed down at the bottom: Arthur Lipstein, Rishi Mulan, Tristan Orchard, Miles Owen, Paul Richmond, and Joe Smith. Of course, one's not expecting you to read all those papers. I'm not expecting you to read any of those papers. But what I want to emphasize today will be the first two, the one that is to appear, which should have appeared about 6 or 7 months ago, but never mind, and the one that came out about a month ago. Okay. So in particular, the plan of the talk is to give you an introduction, explain why I'm doing what I'm doing, and then at the end I'm going to give you a conclusion. Sure. What goes in the middle, I've decided to split up into two parts, which I have creatively called Part 1 and Part 2. So Part 2 is a discussion of five-dimensional Lifshitz gauge theories and so-called Schrödinger symmetry. And I'll explain why, in a conference on M theory, one is remotely interested in such systems. And Part 2 is to introduce an omega deformation, and this leads to, rather than a super Schrödinger symmetry, you get an OSP 6/4 symmetry. If you're familiar, OSP 6/4 is the same supergroup that appears in the APJM theory of M2-branes. So I'm claiming that this is a theory which has OSP 6/4, but it's describing M5-branes. But let me get there first. So I don't think I need to spend too much time dwelling on the introduction, but let me just say it for completeness. So CFTs are, of course, ubiquitous in physics, and particularly in string theory and M theory. And one of the most surprising things, I think, is that we have these theories we know to exist above 4 dimensions, 5 and 6 dimensions. And that's always a challenge, I think, because basically quantum field theory is a central topic in modern physics, and there's simply no textbook understanding of how you would do quantum field theory above 4 dimensions. So it's a big gaping hole in our understanding of the most fundamental set of physical laws that we know to apply to the universe. So there are various approaches, of course, not to say we don't know anything. I've listed some here: bootstrap, deconstruction, appeal to string theory, and DLCQ. So I won't say too much. Bootstrap is bootstrap. It's a first principles approach to superconformal field theories. Deconstruction was actually, I think, the first attempt to construct 6-dimensional superconformal field theories by taking very interesting and peculiar limits of 4-dimensional ones. Appeal to string theory, well, these theories were formulated to exist, and I should say M theory, this is an M theory conference, the string theory and M theory, because they come out of certain limits of string theory and M theory. But we would like to understand these quantum field theories as quantum field theories in their own right, not as some peculiar limit of string theory and M theory. And then I've got DLCQ, not because I like it, in fact I don't, but it's the one that's most relevant for the rest of the talk. So I'll mention what it is in more detail later. And I also wanted to say a few other things. So if you speak to a conformal field theorist, and I don't mean to offend anybody here, but in a way I find there's a certain rather dull approach to conformal field theory. I call the telephone directory approach, which is if you have a conformal field theory with no marginal operators, then basically the solution of the theory would be a list of operators, their scaling dimensions, and their OPE coefficients. And each of one of them would be a number. So it would look like a telephone directory. And that's fine. That's what we're after. That is ultimately what we're looking for. But we all, I think, are accustomed to a much more beautiful approach. Well, let me not prejudice geometric, shall we say, approach to understanding gauge theory with connections and all sorts of lovely geometry that feeds into the fundamental description of the theory. And of course, famously for the 2,0 theory and the M5-brane, we're all sort of hunting around for some kind of notion of what a non-abelian two-form gauge theory would look like. And I've been very naughty here because I have not referenced anyone except all of us, because I suspect that all of us have had thoughts and publications, certainly, about this beast. So one of the issues is, we want to understand these theories, but I want to understand them in a way that, relates to their geometrical structures in gauge theory, beyond Bootstrap, or complementary to Bootstrap, I might say. And the fundamental idea is this notion that if you take the 2,0 theory and wrap it on a circle, that should give you 5D super-Yang-Mills. And suddenly, 5D super-Yang-Mills, you have all the dictionary of gauge theory, non-abelian structures, etc. But a key problem in this whole thing is the lack of a Lagrangian. That's to say, the lack of a six-dimensional Lagrangian which can reproduce the dynamics of the 2,0. And the point I want to start with is that even without asking for these beautiful symmetries, gerbs, non-abelian two forms, what could a Lagrangian look like? What is the playground of a good UV-complete Lagrangian above 4 dimensions? What could it look like? So I know Christian has done some work. I've sinned in this area too, and I think others do as well. But that, I think, is one question you can simply ask yourself. So I'm going to give one answer for that today. And the answer is going to be not what you might think, well, not what comes to mind, which is 5-dimensional non-Lorentzian theories. So what? I mean, what's the problem? So 5D super-Yang-Mills is naively non-normalizable. So Mike Douglas and me and Mike have had this conjecture that, well, actually, maybe secretly it's non-perturbatively well-defined. Okay, it could be true. That conjecture could be true in some sense, but it's somewhat useless because one can't compute with this theory. It doesn't quite know what to do. On the other hand, if you do reduction on a null direction, one of the earliest approaches was this DLCQ. Now, reduction on a null direction means many things to different people, not always very physical. But usually it's meant to be a boost of a space-like compactification on a circle. So here it's not very physical and particularly satisfactory for reasons that I might come back to later. But anyway, in all these sorts of scenarios, the key relationship between the 6D theory, the phone list of phone numbers, the phone directory, and the 5D theory where you have a connection, is that it's the Kluser-Klein, the Kluser-Klein modes, the would-be Kluser-Klein, the momentum modes of the extra dimension, be it compact be it null or space-like, are associated to instanton numbers. So the second Chern number of a gauge field. And in those approaches to reconstructive theory, you need to send the coupling constant to infinity. Now, let's go back to the DLCQ. The null reduction of a Lorentzian superconformal field theory would give you a theory with Schrodinger symmetry, right? So that gives you translations in space and time. It's going to have rotations. It'll have boosts, but not Lorentzian boosts, and a Lifshitz scaling symmetry, as well as a sort of what you might call a special conformal transformation, something like special K. Such theories have been studied in condensed matter physics in lower dimensions, of course, in 3 dimensions, particularly by Son and collaborators. And they're not interested in reconstructing a 4-dimensional theory or higher dimensional stuff. They're just interested in looking at condensed matter systems where they don't worry about not having Lorentz symmetry. That's not of interest to them. And the role of the KK momentum for them would be a particle number or charge. And they usually restrict to a particular sector of that theory, whereas we would want to have the full KK spectrum to reconstruct 6 dimensions. So the important point of point 1 of this talk is that there are UV complete 5D gauge theories which flow in the IR to such theories, to theories with super Schrodinger symmetry. That's what I will spend some time explaining to you. So we can, in principle, have a nice happy UV playground, for at least for the DLCQ proposals. Now, I mentioned that it's not ideal, and one of the problems is that if you look at the correlation functions of these Schrodinger theories, well, they have like the 2-point functions are like the Schrodinger propagator, and the Schrodinger propagator is not spatially suppressed. Right? It has a temporal separation, but not a temporal suppression, but not a spatial suppression, and that's makes reconstructing higher dimensional physics very difficult. And the other problem is, of course, as I've already mentioned, if you want to construct higher dimensional physics, you need to somehow take the infinite coupling limit, and that's easy to say and very hard to do. So that motivates part 2 of the talk, where we introduce an omega-deformed version. So you take these Schrodinger, super Schrodinger theories, and you introduce an omega deformation, and it turns the super Schrodinger group into a group called SU13, which of course you can imagine what SU13 is. What's the benefit of doing this? Well, for a start, you get better controlled correlation functions. They have spatial decay. And also, the way this is constructed, and I'll explain it later, is when you write down the correlations of these functions, you're automatically reconstructing correlation functions of the uncompactified 6D theory. There isn't a null compactification, which you then have to take the limit of the radius going to infinity. You are always talking about the non-compact theory, just in a very weird way. There is a coupling constant, it's analogous to ABGM, is a 1 over k that appears out in front, and we claim that the 6D theory exists at k equals 1. But you could do a large k weak coupling expansion. So as I mentioned already, it's like a 5D analog of ABJM, and the full supergroup, which includes SU13 as the space-time symmetry, is in fact OSP 6/4. So that has the SU13 and the SO5 as an R symmetry. And the claim is that the non-perturbative effects will enhance that from SU13 to SO26, and the SO5 goes along for the ride. And this is simply a different version of the enhancement we see for M5-branes, where in that case it's the R symmetry, which is SU4, and that enhances to SO8. But I would, reason want to sell you if you don't like these motivations. I find it's a weird and wonderful playground away from the familiar territory of Lorentzian physics, which certainly I was raised on for most of my life. So it's quite fun to go and see what's different in these other theories. So I've got a little diagram of what I'm trying to do here. So we start on the top left with some UV-complete Lifshitz gauge theories. And since they're 5-dimensional gauge theories, they have an instanton tower of states, right? Because it's a topological property of a 5-dimensional gauge field, is that there's a one-form current, which is star trace F wedge F. So the first part of the talk, part 1, is this discussion that, well, if you take those theories, you can at least imagine IR flows where you go down to supersymmetric 5D Schrodinger gauge theories. And these are precisely the theories that reproduce DLCQ. Yeah? And hence, they are reconstructing for you 6D superconformal field theories on a null circle. Okay, so that's part 1. So at least we have a happy playground. And part 2 is to introduce this omega deformation that I mentioned, and I'll highlight why we do that. I mean, well, where it comes from, I should say. Why we do that is that I claim that if you deform by omega, then you get 5D theories with an OSP 6/4 symmetry, and that lifts to non-compact 6D superconformal field theories. And as I mentioned already, this is basically just a Wick-rotated version of the kind of enhancement one sees in the ABGM models for M5-branes, namely that the SU13 gets enhanced to SO26 rather than having SU4 enhanced to SO8. So it's a different playground. The physics is very different because you're trying to enhance Lorentz symmetry, space-time symmetry, not some R symmetry. So your starting point is a little bit less familiar. You're in a very weird space, but you have a Lagrangian description. Okay, so let's start with part 1. So what's our happy playground? Well, I'm going to start with this class of theories. So you keep the normal sort of electric fields, so it's FTI squared. The reason for that is you don't want to have ghosts. So normally with higher dimensional operators, you get ghosts, but this is okay because you have a quadratic E squared term in your propagator. What you change is the spatial gradient terms. So you have a df squared term. So this is going to be 4 derivatives rather than 2. So that's sort of your free theory that you're perturbing around. You might wonder why I've chosen that tensor structure. It's a nice tensor structure for many reasons. You can imagine one more type, which is just where there's no contraction on individual indices. So DIFJK all squared. But it turns out that that term is equivalent to the term I've written down plus a cubic interaction term. And so I'm going to choose to work in a system where I'm just viewing the free theory as this term I've written up there, and there's potentially an F cubed term that you have to worry about, and if you wanted to do things more properly, you would have to worry about. But our guiding principle is that this theory has a Lifshitz scaling symmetry. I've obviously thrown Lorentzian variance out the window, but that's okay, because we're not looking for if we're looking to describe the M5-brane, we are not looking for 5-dimensional Lorentzian variance, necessarily, right? We're looking for 6-dimensional Lorentzian variance. So this has a Lifshitz scaling symmetry where time scales twice as much as a space. And these theories are known to be perturbatively normalizable because of the extra power in the propagator. So various authors have discussed this. Harava did a lot of work on this as a toy model many years ago for his gravity, but it was espoused by various people about the quantum properties of these theories. And the key point is that there's a 4th power here, and hence this is what turns your theory renormalizable, yeah? But not Lorentz invariant. Well, you might also imagine scalars and fermions. So I imagine a scalar action which is fairly similar. Everything has the usual kinetic terms for the fermions and for the scalars. But I only introduce, because of this Lifshitz scaling, higher derivative terms for the gradient, the spatial gradients. So that's what I have there. And for the fermions, I have a 2-gradient term. You'll see that there's a lambda here. So I have an overall coefficient of 1 over g squared out front, the coupling, and then each field comes with its own lambda, which is telling you the strength of the gradient terms, if you like. And one of the irritating things about these theories is that each field can have its own lambda. It's like a speed of sound, if you like. And each field can have its own separate speed of sound, which makes them very, well, in a positive level, makes them very rich. In a negative level, makes them very hard to control. But let's not worry about that now. And of course, I could imagine including them in other representations of the Lorentz group. There, I've assumed that they're in the adjoint, but you can imagine how it goes if they're in some other representation. So in that paper from December, Joe and I calculated the beta function, while Harava calculated, we did it with the scalars and fermions. Harava, based on other people's work, already computed it without that, and we agree with his result for beta of g, that's that first term here. So we reproduced his term, and then we were able to compute the correction from the scalars. I should say that this is a pretty horrendous calculation, but I'm going to spare you the detail.
Sorry, how do you know which Lifshitz theory you should start with? Well, meaning Lifshitz scaling. Why is it lambda squared, not lambda cubed?
So certainly you could consider more. But if I take a 6-dimensional superconformal field theory and reduce it on a circle, then I'm going to get Lifshitz with what I call Z is 2 with this scaling. But certainly you might want to try other. So for example, you might want to start, I'm already giving up a lot by starting in 5 dimensions. Why not start in 6 dimensions? And then I think you'd want a Z equals 3 theory, like you mentioned. I haven't looked into that. You can do that. The problem is these theories have been studied in a variety of contexts. For example, just simply in 4 dimensions as ways of regulating the UV with theory. The problem is landing on Lorentzian physics is very tough when you do this.
Right, so that was going to be my second question. So there's a sort of, like shooting upward to see where you go. Is there a general criteria when you can say you would actually get the Lorentzian?
So people have studied this. People have studied this in 4 dimensions. And I think the synopsis is it's maybe possible, but it's very hard to land. What the story that they studied in 4 dimensions is you add these kind of propagators in as UV regulators. and then you ask that your IR theory is Lorentzian. Of course, it's never going to be exactly Lorentzian, it's Lorentzian plus corrections, and then you want to put a bound on those corrections. And my understanding of those people is that because Lorentzian variance is so fundamentally constrained, it's very hard to land on theories where you are within those bounds in the IR to get Lorentzian variance. It might technically be possible, but the literature there is more focused on phenomenology and actually comparing it. And I don't know of any literature beyond 4 dimensions on this. So our goal is to reproduce Schrodinger symmetry in 5 dimensions. And I will argue that we have these flows. I don't know how generic they are. But my point is to embed a certain class of theories into a UV complete theory, just like I said, so I have my happy playground. So the one thing you'll notice from these corrections to the beta functions, of course, the famous sign, it's negative, it's asymptotically free. And the matter fields contribute positively. The fermions don't contribute at all. This is a freak of non-Lorentzian physics, and it's a fairly well-known point, is because you have a dispersion relation for the bosons. It was written here, basically. E squared is plus lambda squared p to the 4th. So E goes like lambda squared p to the 4th. Fine, E squared goes like lambda squared p to the 4th. If I had a fermion, the dispersion relation is just more like E goes like lambda p squared. So E is positive. There are only positive fermionic modes. And this means that when you do any contour integration for divergences, you can always close the contour in the upper half plane and remove all the divergences. So you never get divergences from fermions. This is a result, I didn't reference them, but it's a result of an Israeli group. And that's what we find too. They simply don't contribute to anything. Another thing you'll notice about my fermions here, I haven't said what kind of spinors they are. In fact, they may not even be spinors. There's no criteria here to make them spinors. They could have an index if you like, a flavor index, a spinor index. It doesn't matter. It's because there's no gamma matrix in there. There's no place to put it. And well, I'll come back to that in a bit. So one of the arguments we have, and you can read our paper because it's, the one regret I have about our paper is I didn't find a nice, clean answer for this argument, is that theories of this type, which are Lifshitz but not Lorentzian, they can't be made supersymmetric, and they can't have boost symmetries. I should have a caveat. I said the fermions could be anything. I'm thinking of the fermions that are at least spinors of the rotation group. You can make a supersymmetric version of these theories, but where the fermions are themselves space-time vectors. Sorry, space vectors. There's no spin statistics theorems if you give up Lorentz invariance, so you can have perfectly good theories where psi here would be a vector of the 4-dimensional spatial group. And then you can make it supersymmetric, and the supersymmetry generator is a scalar. So we give examples of those in our paper, but that's not what we're really after here. So we claim that these theories, they're UV, weakly coupled, and they're renormalizable, so that's all good. So we want to introduce flows, and the idea is we're going to introduce a flow by adding this term. So M here now, from a Lifshitz point of view, is like a mass term. It's got a positive Lifshitz scaling dimension. So in the IR, it's going to infinity, and I add to it f plus star f squared. So the claim is that in the IR, you're going to constrain to the vacuum, to the minimum of f plus star f squared. So you're going to constrain to anti-self-dual gauge fields in this case. And so you might imagine, and we give a slightly better argument than I present here, that the effect when you go to the IR then is to have a term like this, where there's a Lagrange multiplier, which puts you down onto anti-instanton moduli space. And then, if that's the case, forget that term, that's the term I said didn't exist. If that's the case, then this term becomes irrelevant, and you can simply find this as your action in the IR. Yeah? So there's the electric field is untouched, and then you have this Lagrange multiplier constraint that puts you onto anti-self-dual gauge fields. I could also imagine deforming scalars in a similar way. I would add an m-squared term. So this is like adding the Lorentzian gradient terms. But rather than trying to recover the Lorentz invariance, I want to say that this is a relevant operator, and it's going to dominate in the IR and constrain the system. If I do it like this, well, this term, in order to, if m squared goes to infinity, you'd think this just gives you a scalar that's constant. But what you can do is you can invent a new scalar, which is to rescale it by phi. So then, of course, you get a 1 over m squared here, and nothing here. And then you might imagine that the IR theory is simply described by something like that. So we have a bigger discussion about this in the paper, of course, and we discuss how you could do fermions. But the bottom line is you might get theories where the scalars have a contribution like that, and the main player, the gauge fields, have contributions like this. So the point about these is these do have Schrödinger symmetry. So if you imagine a boost like this, a Galilean boost, then your scalars are invariant, your spatial gauge fields like that, and then this is not surprising. What's somewhat surprising is this Lagrange multiplier has to transform like so, and then the action changes by this term, which is just trace f wedge f, which is a total derivative. So in these theories, you have a boost symmetry, but the action is invariant only up to a boundary term, a topological term. So remember, if we go back to the ABJM analogy, the M2-brane analogy, in that case, you have a Chern-Simons theory, and it's the gauge symmetry that you have to worry about because of the Chern-Simons term. It's the gauge symmetry that gives rise to lots of subtle effects and feeds into these monopole operators that can enhance the symmetry. Here, it's actually the space-time symmetry. It's the boosts which have the subtleties that you have to worry about. And, well, we'll come back to that later. There's also a special conformal transformation, which is very similar to what I've written here. It's just that what was vi here was just a constant parameter. You replace it with omega times xi, and that's also a symmetry. And you can make them supersymmetric, yeah, with spinor fermions. Yeah? And I'll come back to that later when I give you an example. So what's the physics of such a theory? Well, of course, you would integrate out the Lagrange multiplier, and that tells you that f is minus star f. And you could solve that using ADHM. So in principle, at least, you can write the AIs as a function, explicit function of space and moduli. And then if you put that back into the action, you simply get a sigma model where G alpha beta is given here is the metric on instanton moduli space. So the dynamics of this theory in the IR is just quantum mechanical motion on the instanton moduli space. And boom, that is the old DLCQ proposals. Yeah? So the claim here is that the UV completeness of a DLCQ description of the M5-brane, the six-dimensional 2,0 theory, ironically, is a five-dimensional non-Lorentzian Lifshitz gauge theory. Okay? What time did I start?
3:15.
Ah, okay. So I've got another 2 hours. Half an hour.
Sorry, just a simple question at this point. So after compactifying one more dimension, can you regain Lorentz invariance? I think you said.
No, it's gone for good in this picture.
But isn't that, don't we want some theory that gives us 4D Lorentzian theory? No?
Well, I think to get it like that, you'd have to go up, first reconstruct the six-dimensional 2,0 theory, and then compactify it. So I think if you took the Lagrangian that we had here, and you can take this Lagrangian and you can compactify it. That's easy, right? But that's not going to give you Lorentz invariant theory either.
Not even in some, not even secretly?
Well,
Does it mean we lost something of the 60 theory then? Or?
No. So having said that, let me be clear. These Lagrangians don't have Lorentz symmetry. The claim is that if you put them into a path integral and do things cleverly, you can reconstruct a theory that has Lorentz symmetry. Yeah? And if you put these theories on a circle, first of all, I would want you to keep the Kluser-Klein tower. That's important. But in principle, you could do that. And then if you put that back to the path integral, yeah, you'd hopefully still be recovering the six-dimensional Lorentz symmetry. But if you just did textbook dimensional reduction, I don't think you're going to reproduce Lorentz symmetry. William?
Sorry. So the picture you described, you seem to be giving a picture of an IR duality, two different theories that somehow flow to the DLCQ. How do I know that they're actually the same in the UV?
What are the two? The 2,0 on it.
Yeah.
Well, okay, so that's the million-dollar question, right? So there is the 2, so you're saying, okay, there's the 2,0, which I could put in a null circle
Yeah.
and reduce it, and that gives me a DLCQ.
Yes.
And then there's this
The 5D.
Lifshitz 5D theory, and I'm claiming it can flow down to the IR and give you DLCQ. So they give you the same IR, well, I would say that our discussion is probably fairly tight. That you take this Lifshitz gauge theory, there are flows that give you this instance on moduli space. That, I think, is reasonably solid. The claim that you take the 2,0 theory and you put it on a circle, a null circle, and you get DLCQ is this conjecture of Seiberg et al. From 2 decades ago. And informally, I believe it, by the way.
But my point is, independent from that fact, which you demonstrated in IR duality, we have many examples where you have 2 different theories in the UV are genuinely different, but in the IR they're the same. You could call it universality or whatever words. So how do I know that? I mean, even the 6D theory itself has other description. There are other, you can have 6D to 4D, and then you can have 4D to 4D. So there are many examples of IR dualities.
Yeah. So I agree. Yes, in that language, it certainly is an IR duality. But the million-dollar question really is it true that the DLCQ, that if you took the 2,0 theory on a null circle, you get instance on quantum mechanics? Because that's part of the how do I go the other way? How do I reconstruct the 6D theory? Because we simply don't know what the 2,0, or at least we don't have a strong enough handling of it to know what it is in the IR. I mean, there's various conjectures, and I think we all believe them, and I'm not disputing them.
Okay, but the Lifshitz model is not giving a model of the 6D theory itself. It's just giving you a model of the DLCQ.
It's just, yes.
Thank you.
Yes, I would agree with that statement. Chris?
Just following up on that discussion, your 5D theories don't seem to care much about the fermions, but in the end, you're interested in reconstructing a theory which cares crucially about the fermions. For example, the 2-0 theory probably wouldn't be conformal. Well, there's questions about whether it have superconformal and so on without that. So, what extra ingredients would you be needed to put make the theory care about the fermions?
Yeah, well, of course, this is an excellent question. I might defer it to the end of the talk because Hi, okay. Well, now I'm going to break out into song. Okay. So one thing I'm not really going to be addressing here, because it's the elephant in the room, is how do you actually reconstruct the 6D theory from these 5D Lagrangians? I have lots of things I could tell you. Lots of those papers are all about that. But it has to play with how you deal with non-perturbatively with instantons and so-called instanton operators. And that's where I would expect supersymmetry to be absolutely crucial. So we have these classes of theories. I claim that they're UV fine and that we should be able to handle them. And somewhere in that space, there's a direction that's going to lift you to a 6-dimensional Lorentzian theory. But it's not a generic thing, I would have thought. It's going to be very finely tuned. Well, maybe finely tuned is the wrong word, but it's very subtle. And I certainly would expect that would depend on the fermionic structure. I mean, another thing you could say is, I haven't specified the gauge group. But we know that the 2,0 only exists for ADE gauge groups, but I could take, SO14 or something like that. And everything I say today follows for SO14. But that doesn't lift to the 2,0. Of course, it lifts to the 2,0 on a twisted compactification. So there's hope that you could make that work. Okay. So that makes me come to part 2, which is to try to do better than DLCQ. So how did we get to this modified DLCQ type construction? So we started the following way. So let's take 6-dimensional Minkowski space, which I hope we'd all recognize as this, and I've done a strange change of coordinates to write it like that. And the point is, if I start with a conformal field theory, then I can do a conformal transformation and remove the denominator term, and I can just imagine putting the M5-brane on that spacetime. Well, why have I done that? It's because if you look at this mapping, the range of x plus is restricted. It's in an interval. Now, no one said it's periodic, but it might be, at least in some sectors, enough to consider a periodic expansion in x plus. But I'm reconstructing the non-compact Minkowskian direction in this way. The point of doing this, it's rather contorted, is that if you want to reduce M5-branes on a circle, you need to have an isometry. And this has an isometry. D by dx plus is an isometry. It's not an isometry up here because of the conformal factor. And it's not an isometry if you do more various other types of weird conformal coordinate transformations. But if you do it this way, you get an isometry. So you can do a reduction. So we would like to, think of x plus and then p plus as discrete, as I said, for certain boundary conditions. We diagonalize it. So what happens to SO26 when you write it in this weird coordinates and make p plus discrete? Well, SO26, the stuff that commutes with p plus, well, p plus commutes with p plus, and that's where you get your SU13. It's the rest. And here I've written in glory detail the relationship between the generators of SU13, which are without the hats, and the generators of SO26. And you also break, you don't break, you preserve 3/4 of the superconformal symmetries. Roughly speaking, you could think of it as following. You have 16 normal supersymmetries and 16 superconformal symmetries, and you're going to break 8 of the superconformal symmetries, because if I think of it in the flat Minkowski direction, these are the 2 types of symmetries, supersymmetry generators. You have to ask that they are invariant under x plus, and you'll see that the epsilons are invariant under x plus, and half the etas are, because the etas that are annihilated by gamma plus will not depend on x plus. So that's why you preserve 3/4 of the supersymmetry. Of course, we didn't pull this out of a hat. We got it from a holographic construction down to Pope et al. You showed that ADS7 can be written as a time-like Hopf vibration over CP3 tilde. Let me know. Well, the details are here. And the point is that this is just ADS7. And if you go to the boundary in the way that where phi here is like the radial field, so if you go to phi equals infinity, you recover this boundary metric, which is the metric I had before. And that's just the classic, right? I mean, ADS-CFT, when you go to the boundary, you land on Minkowski space up to a conformal class. And this is just a different choice in that conformal class. But it has a more natural connection to ADS7, which, although I haven't used, we hope would be useful in the future. So what's the action? Well, this is what you get, and it's broadly of this type that I mentioned before. So there's the electric field squared. X minus is what I called time before is now x minus because it was at one point in null direction. And then this is the scalar term that I mentioned. Here's the constraint that puts the gauge fields onto self-dual, and then here's the fermions, which I didn't hardly mention at all. And these are, of course, spinners of SO4. So if there's some hats and curly things, what are they? Well, the hat is this twisted thing by omega. So omega appears here. It starts off life as simply as a coordinate transformation. It's in here. And what's called R is because omega squared is minus 1 over R squared times the identity. So that's what a hatted derivative is. And then the curly f is the normal f plus some omega deformed stuff. And G is just self-dual. So this is a cute system. It's got torsion. If you look at the commutator of 2 spatial derivatives, that closes into a temporal derivative. But it's got this SU13, it's got an SO5, and it's got the 24 supersymmetries, so that's OSP64. So this is the Lagrangian you can write down with OSP64, and it's got a topological U1, all 5-dimensional gauge theories do, as I said. We have also constructed versions of this which might be associated to the 1,0 superconformal field theories. But for the sake of simplicity, I'm going to talk about the M5-brane here, so 2,0. So that's our action, and it has all these symmetries. It's a bit of a weird beast, but it has nice features. So let's look at the correlation functions. So SU13 plus a U1 places non-trivial constraints on correlation functions, like in any conformal field theory. And we worked out what that is. So what happens? So first of all, I have to introduce this coordinate Z. So Z here, the real part of Z is, and A and B refer to 2 different points. So it's the difference in the time, the real part, plus an omega deformation involving the difference, well, the positions in X. And then the imaginary part is just the length squared of the distance between X and Y in space. So this guy will feature heavily for the rest of my talk. And the reason is when I write correlation functions out, they're quite nicely expressed in terms of Zs. So you have something that tells you that the sum of the p's must vanish, this p plus eigenvalue. Then you have this bit here, which is very similar in spirit to 2-dimensional conformal field theories. It's the suppression factor. So the alphas, I didn't give you the, are just the usual sort of things from the scaling dimensions, right? Like delta A plus delta B minus the sum of the deltas and all that sort of stuff. And the p's are the eigenvalues under p plus. So you get a suppression here, 1 over z squared, given by the conformal dimension, the Lifshitz conformal dimension. And then you get a complex phase, which is given by the p eigenvalues, the p plus eigenvalues. But then there's this thing you don't know. As always, this only buys you so much. There's a generic functions, and what's it a function of? Well, at 4 points, you have the usual problem that there are cross ratios. So it's a function of the cross ratios at 4 points or more. But actually, it's already not fixed at 3 points. At 3 points, you have a function of this weird combination. This is a generalization from omega. So these things were known for omega equals 0 for the Schrodinger symmetry, and this is just some kind of angle phase. And when you take omega to 0, you reproduce the old results. But anyway, you have this one known, at 3 points, you have one unknown function here. So I know what the alphas are. I haven't written them down because they're just determined by the deltas of the operators. So alpha A, B, N. Maybe I can write it. I'm going to get it wrong, but it's something like this. It's the usual kind of expression you see in a conformal field theory. Okay. Okay. So that's great. Of course, the one thing well, is it great? I don't know. Anyway, the one thing I've sort of hold the wool of your eyes is I've talked about this p plus a lot, but actually p plus is this topological number associated to the instantons. And if I construct something out of the fundamental fields in the action, they're all going to have p plus equals 0. So I need to find a way to get p plus in there. And one of the observations is that SU13 is only a symmetry up to terms which are non-zero if the instanton number changes. So I remember I told you that these boosts are only symmetries up to a Chern-Simons term. So it turns out that if you change the instanton number, then that term is not 0, and you will break SU13. But you can restore it, and you can restore it by introducing a notion of an instanton operator, which I'm willing to confess is not poorly poorly understood, where you insert an instanton at a point. Now, I don't want to. I could spend 3 talks trying to describe this and still not make any sense. But there is some notion of instanton operator where you take a point in 5 dimensions, you surround it by a force sphere, and you demand that or on that force sphere there is an instanton number. It's an analog of monopole operator. So you have the same idea here, and what you find is that these will therefore ruin your SU13 because you've added topology changing things, which means that the action is not invariant under SU13. But if you assign the instanton operator as a transformation rule under SU13, you can restore SU13. Yeah? So we find that you can keep SU13 plus U1 as a symmetry of the path integral now, because now I'm having to tell the path integral how to behave under SU13 transformations. And then you see that these instanton number operators have charge n over r under p plus. So the idea, of course, as I mentioned several times already, is that we want to use these things to enhance the SU13 SO5 to SU16 times SO5. So this is, again, I've said it several times, I'll just skip in the time, that in ABJM you have a U1, and the charge is carried by monopole operators, and an R symmetry, and that's supposed to enhance to an SO8 R symmetry. So here I've got a U1, which is carried by instantons, and I've got an SU13 spacetime symmetry, and I want this to enhance to an SO26 spacetime symmetry. Supergroup-wise, it's the same thing. So how might I do that? Well, the idea is to dress up, to make a 6D operator out of 5D operators by inserting an instanton operator and then an e to the minus n x plus. I put an arbitrary function in here because I don't know enough about instanton operators to tell you what function to put. Let's hope it's 1. But for the sake of argument, you can put it in there. And again, if I knew everything I was doing, I would still be free to put any function I like there. And then it's easy to see that the action of P plus on this 6D operator is what you'd expect. And that doesn't matter how you define the F's or the I's. Well, you need the fact that the I's have P plus value n over R. So this constructs for you 6-dimensional operators in the sense that they have this. What, of course, you want to do is to construct a theory that has Lorentz invariance, and that's a very much more restrictive statement. So these theories, if everything I tell you today works, they would still offer you the opportunity to construct a very weird and wide class of 6D theories, only some of which would have Lorentz invariance. But maybe that's a good thing. So I just brushed through it. You want to have this operator have to have a good 6-dimensional scaling dimension, so that puts various constraints on it because that's the 6-dimensional tiltation operator. And you know what the 2-point functions look like because I've told you they're ambiguous. And this tells us sort of constraints on what these F's have to be to make it work. And then what you find, I'm just going to rush ahead, if you take the 6D operator and expand it out in terms of these 5D correlation functions, you sum it up, and you will indeed get the non-compact 6D 2-point function. Right? On the nose, provided that indeed you can have these operators which have these correlation functions I mentioned before. Which, at the end of the day, would, if nothing else, boils down to some choice of those FNs that I've told you about. Okay. I want to mention a brief thing. So where the hell is DLCQ in this? Well, you can take a limit. So I've missed it actually. This omega, well, there's an R in the omega, and we can show that R should basically be thought of as some fixed R divided by a K. K is an integer. And it turns out that if you can take the K infinity limit, that's basically, so normally the K to infinity limit, the R to infinity limit is turning off omega, because omega squared is 1 over R squared. So sending R to infinity is turning off omega. So you just set omega, and everywhere in all the formula, you could just set omega to 0. It's never in the denominator, it's always in the numerator. You just set omega to 0. But if you do something slightly different, you send R to infinity, well, with R over K fixed, and then you just keep each kth Fourier mode. So you're keeping a selection of Fourier modes. Basically what you're doing is you're holding the lowest Fourier mode number fixed. And here's sort of a diagram of it. We have our 2 pi r, and then you're slicing it up like so into Fourier modes, and you're keeping this distance fixed. So you're sending k to infinity and r to infinity such that this distance is fixed. That reproduces DLCQ. You just have the underformed theory that I mentioned before and includes the Klein tower. The action, of course, you're just turning off omega, and so that's easily done. The action, you get this, and that's precisely in that class of actions that I argued before came into the IR of the Lorentzian, of the Lifshitz theories. And we're back to the DLCQ prescription. But it's, from our perspective, it's a very degenerate limit because you lose everything in the correlation functions. The correlation functions go to normal Schrodinger correlation functions, so there's no spatial suppression. You will not have this reconstruction of a 6-dimensional correlation function. At least not in any simple way. Because, of course, DLCQ, we reproduce things with this null compactification, and we're not doing that. So the last thing I wanted to mention is this paper that hasn't come out, but should have come out 6 months ago, is to look at 3-point functions. So I showed you that the 2-point functions in principle work, which is nice, but of course, as we all know, 2-point functions are heavily constrained anyway. And so we find that you can get the 2-point functions of a 6D CFT. So there's a nice paper by Son and Golkar, where they're looking at 3+1, I think, and Schrodinger theories. And they show that something nice happens if the conformal dimension is d over 2. For them, d over 2 is 1, and that works nicely for them, kind of. For us, d over 2 is 2, because it's the spatial dimension. Operators with dimension 2 are trivial, because at least the only scaling operator I can think of with dimension 2 in this theory is trace x, and that's just the center of mass coordinate, and it's free. But actually, if you follow their argument, you find something slightly different. So what's their argument? You do an OPE expansion, so take 2 operators and you close to each other and you expand them in terms of an infinite expansion of operators on the right hand side plus their descendants, and then these OPE coefficients. And then there's a well-known trick which you can expand everything with respect to the various operators in your theory and reinsert into your expansion, and then you can read off differential equations, so these C's can all be determined by differential equations acting on C0. That's a well-known trick in conformal field theory. If we do that, we'll get, and we do it in particular with this operator, n+, so you get some differential operator, which I've written here, acting on C0, and some other stuff acting on C0, is something acting on C1. What's interesting here is that this operator this is not invertible necessarily. So if P takes this value, then this thing is null. You can kill it off. So you can hit the left-hand side with this operator and you get 0, which means you get a differential equation for C0 alone. And you can determine what it is. And, well, in the interests of time, let me just say that you can determine it. You have a differential equation for it that determines its holomorphic bit. You don't know its anti-holomorphic bit, but then you do know what its conformal scaling has to be, so this fixes it. So if one of the operators on the right-hand side has P plus equals delta over 2, then you know what the C0 is for that OPE expansion, and it's given by this form here. And if you know that, then you can compute 3-point functions, because you take your generic 3-point function, and then you take x goes to 0, this guy goes to that guy, so you replace these two with their OPE, which gives you that sum that I was mentioning, and then you get this C in here, it's in green. Now you have a 2-point function, but you know how 2-point functions behave, but then now you know how that function behaves, so you get this one and that one and this. And it's all just boils down to the fact that if I compare against my general result was for a 3-point function, there's all these horrible factors and this unknown h function. Well, in this limit, this h function reduces to this. H reduces to this. These other prefactors are all here. And you can compare this, this, and this with this, and it allows you to read off the h function. So in this limit, we know for operators where they satisfy this bound, we know what the 3-point function is. And the nice thing about this, of course, is it's precisely the 3-point function that you get from 6 dimensions. Yeah. So in other words, all of the 5D 3-point correlation functions containing one operator with p plus equals delta over 2 are those of a 6D theory. Yeah. But of course, there's many others, which may not be. All righty. So I guess now it's time to do the conclusions. I'll try to remind you of what I've been talking about. So I hope to have convinced you that at least there's an interesting class, a novel class of field theories. Typo there. They're in 5 dimensions, but the whole raison d'etre of studying them for me was to try to get a handle on 6-dimensional CF superconformal field theories like the 2,0 theory. So in the first part of this talk, I tried to convince you that in this non-Lorentzian setup, you have a class of UV complete 5D gauge theories. You have a playground in which you can embed your physics and construct quantum field theories. They're not Lorentzian, but they exist. And they exist with some weakly coupled IR UV completion, as we normally understand QCD, for example. It's quite a rich place, or scary would be another word, because as I mentioned, if I look at the beta function calculations that I did way back, first thing you might ask yourself, is there an analog of NF equals 2NC? And the answer is no. Where is he? So I wrote the beta function here. The problem is there's the lambda here, and there's the lambda x for the scalar here. So if those are different, then the same matter content could be asymptotically free or asymptotically not asymptotically free, depending on the relative values of these lambdas. So the flows in this space will be much more complicated. Of course, you might have a symmetry principle, for example, the scalar supersymmetry, which tells you the lambda equals lambda x, and then you would have an analog of NF equals 2NC. And this, by the way, is big enough to fit the 2,0. I think you find out that you can have up to 6 real scalars in the adjoint and have UV completeness. All right. No, there's the song coming. Okay. So we argued that those theories are not particularly interesting in terms of their symmetries, but in the IR, they can flow down to this class of theories that we are interested in, at least I'm interested in. So these are this very superintegral Schrodinger theories that are associated to the classic DLC-Q. But then part 2 was to emphasize that there's this omega deformed DLC-Q, which is we hope to be the M5-brane analog of ABJM, or the M2-brane story. So introduce an omega deformation. This helps us because we now have correlation functions that are decaying spatially, and in fact you can reconstruct the 6-dimensional correlation functions as an infinite sum. We hope that there's nice structure here. One of my favorite things to talk about, but I've spared you this, is you can ask yourself, what's this curly f equals star curly f, this twisted omega deformed instanton equation. It turns out that system, which is of course highly nonlinear, you can put in a Topf ansatz and it linearizes. So I can give you an infinite class of solutions to that thing. And it describes, what you find is it describes world lines of instanton particles that are arbitrary, and the size and position of the instantons can change as you move along the world line of this particle, this object. And so that's the constraint surface where the dynamics lives. And it was remarkable to me, and hints at a deeper structure, that you can take this weird nonlinear gauge theory equation and linearize it. I would love to know if there's an ADHM construction that mirrors the Topf construction. Now, formally, so one might ask about integrability. So that was an indication that there's something going on deeper. Integrability, well, formally, the string background, because you can do a string background for this, because you can reduce on a circle, it's formally the same as the ABJM one, but it's just Wick rotated. So my friends tell me that shouldn't be a problem, but it's not my area of expertise. I would note that my student Tristan wrote with Arthur a paper where they showed that there's a Yangian structure Now, they didn't show that there's a Yangian symmetry, but they showed that there's a Yangian structure of these variables of this OSP64 in 5 dimensions. But I've just told you everything I know about Yangians, so don't ask me anything about that. And we saw that we can reproduce the DLCQ picture. Of course, you lose all the nice properties, and we can't readily construct the non-compact theory. On the to-do list, there are big issues. The first thing would be to actually compute something. That would be nice. And the problem is, and that's step 2, is to do anything non-trivial in this theory. It's not really weakly coupled. I mean, I've embedded it in some UV weakly coupled theory, but the theory that we're interested in is not particularly weakly coupled. It requires immediately knowing how to work with the instanton operators in the non-perturbative sector of the theory. And so we need a better understanding of instanton operators. So we know a lot about how they're constrained, but not how to compute with them. Another question, and this is why I deferred Chris's question, is there's presumably a lot that we can get out of here that's junk. Well, not junk, but not 6-dimensional superconformal field theory. So what's the rule book? How does it work? So, for example, the role of the fermions, the role of the gauge group. My current hope is that it all brushes under what is meant by an instanton operator. I think the rest, these theories I would claim are solid, but when they reconstruct 6-dimensional theory, I would like to understand from the ground up. But on the positive note, I like to think that this is interesting in novel structures, and I'm hoping that since I was last chair 3 years ago, just before COVID, I thought that maybe after the next pandemic, I can come back and tell you all about the instanton operators and how to compute with them, and it's all going to be done. So.
Won't be a pandemic soon, and we won't need that, hopefully. Further questions for Neil? So I have a question. You presented ABGM and your perspective as being, in a way, both embedded in OSP 8/6 and there
6/4. Yeah.
4, yeah. And then there, and one is R symmetry, one is space-time.
Yeah.
Dual in a sense.
Yes.
To what extent are these unique? Can one start playing with the signatures further, since you seem to be okay with losing symmetry?
Yeah, that's an interesting question. So, of course, from the gravity side, it's ADS7 cross S4 versus S4 and ADS7. Right? It's just a question of where you put the time variable.
Right.
Yeah.
But there are other variants, right?
But
this, I think, has this, what is it, M star signatures? Can these kick in, maybe?
Maybe. I mean, so certainly one might. So there is a question of if you give up. So I've got a couple of comments. If you give up Lorentz symmetry, you have opened Pandora's box. So you might ask yourself, what am I allowed to consider? Of course, Schrodinger is fairly well motivated, right? If there was a condensed matter physicist in the audience, that's all they do. Or Galilean symmetry. Schrodinger, of course, is just normal Galilean physics plus a scale symmetry. And a superconformal, and it boosts. Yeah, anyway. Yeah, it begs the question what kind of field theories you could come up with which have rich structures, supergroups, whatever, but what's their space-time symmetry? So here we have SU13, so that's a bit weird. You can also do SU1n in general dimensions, because this trick I told you of conformally compactifying Minkowski space and reducing down by 1 dimension, you can do in any dimension, and you could make it supersymmetric in any even dimension. And then, so this, in principle, you can construct SU12 theories in 3 dimensions, which would come from reduction over 4 dimensions. But, so that's SU1n, but I don't know if there's other groups. And as for the 2A star theories, way back, in this holographic picture, I didn't dwell on it, but if you see the x minus direction is here, and that's the minus sign. So in the ADS7, in the bulk, this is actually a time-like reduction. So the 2A dual is 2A star.
Okay. Yep. Yeah, thank you. Sounds good. Urs?
I saw on the archive, I'm not sure if you mentioned it, you have this article with with Orchard on where you specifically refer to 1,0 theories in 6D and relating them to 5D theories. I'm not sure if I missed it.
Yeah.
It seems to. So does it play a role after all? I mean, could you comment on this? There it seems you're specifically relating to 1,0 superconformal symmetry in 6D, whereas here you were speaking about 2,0 or?
So everything I said here would apply for 1,0 as well. Because all I used is the existence of superconformal symmetry in 6 dimensions.
Or maybe then to ask, so what is it in that article which has 1,0 in the title? What is it specific about 1,0 there? Is do something different? Or?
Yeah, so what we do in that paper is we take these actions here. So this is the action that we get from the M5-brane in this weird reduction. And these all live in, everything lives in the adjoint. And I have my gauge field, 5-dimensional gauge field, and 5 scalars and fermions. What we do in that paper is we say, what would we get if we had a 1,0 theory? So if you have a 1,0 theory, you would get, these come from the tensor multiplet. So the tensor multiplet in 1,0, you'd still get this. You'd only need one scalar. And then you'd have fermions that are in the adjoint. But then you could add hypermultiplets. So we generalize this action to theories where you have what would be associated to a tensor multiplet and generic hypermultiplets in arbitrary representations of the gauge group. And those theories have, well, half as much supersymmetry, but they still have the SU13 symmetry.
Okay, thanks.
So the 2-0 theory is a relative theory. So there is a bulk Chern-Simons theory which controls a great deal of what happens to it, like anomaly and anomaly structure. And from the CFT point of view, if you study the correlation functions of the currents, you should see also the anomaly coefficients show up. Can you match any of those things? Can you keep track of those?
I would love to, so I haven't got that far. So what I'm hoping to do soon is to reconstruct the fermions. So this has all been bosonic, so I don't think one's going to see much. Well, you can even worry about the chiral, the anomaly.
Yeah, the B field is a bosonic field.
So I've concentrated everything on, for reasons I think you can understand, on scalar operators.
Okay.
I haven't done anything yet with something that's not a scalar operator. And that's where I would hope to be able to fix up some kind of anomaly.
Okay, is there even hopes of reconstructing the currents?
There's hope.
Because
There's always hope.
That's probably the more direct way to see them.
I think that's a good suggestion. It becomes computationally a bit tricky. Although, just niggly, like, because you've really, this transformation, you've really kind of messed up the Lorentz symmetry. And, where is it? Here. You have to undo this coordinate transformation.
Yeah, but you have part of the R symmetry that's around.
R symmetry is good. It's all there.
Right.
Yeah.
So, but you have currents for those guys.
Yeah.
So you should see the currents even in this
Yeah.
5D DLCQ limit.
Yeah, maybe that's a good one to look at. So you say the word current, but of course current is one form, and so that means you've got to piece up what are the various components. Like, so for example, why am I worrying? So if I look at this action here, where was it? This is the simple action.
Mm-hmm.
From this is all fine. Well, if I think of it from the 6-dimensional point of view, F and G and Fij are all components of the 3-form field strength. So if you do anything that's like a Lorentz transformation, these guys all have to somehow package together.
But if that Lagrangian has the symmetry, then you should be able to compute the currents.
Yeah.
The question, I guess, is how to reconstruct the 6D currents with these instanton operators that you don't know. Is that the issue?
That certainly would be an issue, but I have to confess I haven't even got that far yet. because I don't even know, I haven't really looked at even how you'd construct something that's not a scalar in 6 dimensions.
Okay, thank you.
Great. One more question. See you.
I've got a question on the 1,0. You have been mentioning hypermultiplets and tensor multiplets, but what about vector multiplets?
Right. So we ignored those on the grounds that they're not naturally conformal in the 6D theory. So I don't know how we would incorporate them in our method. So our technique is, well, I think you probably would agree that this is all a little obscure and a little peculiar. And so what happens is you start with a mythical sort of tensor multiplet, and then when you reduce it, what happens is that it splits into this Fi minus, Fij, and Gij. That's H. Those are the components of H mu nu lambda.
Right.
And then there's a gauge field in there, which is, in some sense, components of the associated 2 form, B mu nu. And that gives you the gauge structure in the reduced theory. If I started with a gauge structure in the higher dimensional theory, well, I wouldn't know how to do that keeping conformal invariance.
Right.
And then I would get another gauge thing down here. And it doesn't, I haven't looked at it too much, but it doesn't look like it's going to give you something very pleasant.
How many scalars are you considering there?
Well, so this one is the 2,0, so there's 5 scalars.
Right.
But
in
we
the
have
1,0
where you have an adjoint scalar, a single real adjoint scalar, and then you have hypermultiple, so 4 complex scalars in any representation of the gauge group, including reducibles.
But you also have scalars from the tensor multiplets.
There would be one.
Ah, okay, one tensor multiplet. Okay.
Well, each tensor multiplet would give you one scalar in this construction,
right, one
and
real
one
scalar.
vector,
Right,
and one Gij.
right. Okay, thank you.
One question by Chris, I think.
Thanks. As you emphasized at the beginning, most 5-dimensional gauge theories don't really seem to make sense, and there's only special, as a quantum theory, and there's only special ones which have ultraviolet fixed points either in 5D or 6D, where you've got instanton operators which enhance either the flavor symmetry or the Lorentz symmetry, which give rise to consistent theories. So presumably most of your non-covariant theories would correspond to things which wouldn't have a covariant either 5D or 6D sensible theory.
Yep.
Is there any way of, can you think of any criteria which might tell you which ones might make sense as a covariant field theory, either in 5 or 6D, and which ones are because it seems you seem to have a lot of swampland there.
Yes.
And you're trying to find just a very few special points, which really makes sense.
So I agree, and by covariant you mean Lorentz invariant.
Yeah, either in 5D or 6D.
Yeah, in 5D.
So a sub question of that is: can you understand within this framework the 5D and ultraviolet fixed points where you get enhancement of flavor symmetry?
Yeah. So the short answer to your question is I would love to, but no, I don't. I mean, I think that is, to my mind, that's like one of the key questions anyway. Is let's suppose you grant me everything I've said here, and we're all happy, and we can all go away and compute with this class of theories. The question is then, these allow you much more than just shooting for Lorentzian 5. Well, these are great to produce Lorentzian 6-dimensional theories. This trick I've used, I can't use in 5 dimensions. So it doesn't even, I don't know of a way to apply it to a 5-dimensional theory. Yeah, and it relates to a bit, if I want to be fashionable, to these fractons and stories. Like if you open up field theory to more generic concepts, then I would claim it has a class of field theories in the sense that you can compute correlation functions and they exist. But if their space-time structure is so alien to us, what are the rules of the game? Because I am shooting for small special cases in this much larger class.
Great. Let's thank Neil again for the very nice talk.